Hello everyone, welcome back to ECE410 Power Electronics class 10. In this class we're going to talk about two different topics. Part 1 I'm going to talk about boost buck converter. Even in the last class we talked about buck boost converter. Now we're going to talk about boost buck converter for the part 1. And part 2 we're going to talk about discontinuous conduction mode. So let's start with the part 1 here. So boost buck converter, you can see that your input is boost, output buck. So how do you put them together, and what will be the polarity of the output voltage? So boost and buck over here, when you combine them together, right, you can make this one reverse, upside down. Then your polarity came, so positive goes to negative and connect in series, right? So that means you're connecting both in series over here. Both these two voltages will be connected in series over here. Then you have some switches you might not need, like this one here and this one here, redundant switch. So you can get rid of them. So we have only this connection with this switch over here and this over here, and in between you have a voltage transfer over there. So that means a boost buck converter does not use the current element for energy transfer. It uses voltage element for energy transfer, which is the capacitor. Remember that buck boost converter, we have inductor to transfer energy. Over here we're going to use a capacitor to transfer energy, because we have the both side is current source. So you need to current source to voltage source, current source to voltage source, and voltage source to current source. That's where the transfer happen. In buck boost converter, your voltage source to current source to voltage source. All right. So voltage source is energy transfer source, as I said. Now, if we remove that, that's what it is. So as I said, this is the one here, your energy transfer source there, which is the capacitor. So you're transferring. This one here is a current source, because the inductor will keep the current constant. Then becomes the voltage, and voltage becomes the current here. Then this inductor also keep the current constant. So current source to voltage source to current source. That's the boost buck converter. Okay. So your left switch could be forward conducting and forward blocking. Right here we'll call it switch number 1. Okay. And right switch would be forward conducting reverse bias, which is diode. I will call it switch number 2. So let's get to internal analysis over here. So as you know that switching are complementary. So Q1 plus Q2 should be equal to 1. So 1 is on, 1 should be off. And your current through this device over here, when switch 2 is on, which is number is here, we call it number 2, we call it number 1 here. When switch 2 is on, input current actually going through this, right? So switch 2 is on, input current going through the capacitor. And when switch 1 is on, your output current over here, so output current would be coming this way, right? Output current is going through the capacitor. So transfer current there would be Q2 I in minus Q1 I2. So then your your power, you can multiply by the voltage across the capacitor, which is VT, which is always constant. This voltage is always constant. So that is your power, transfer source power, which we want 0, because we don't want to lose any power in the transfer element, right? So this power should be 0. If that is 0, that means what I can get here is that I in D2, like average switching time Q, average time the Q is on is D2, D ratio, minus I out D1 equal to 0, right? So that is, if this is 0, that means this is the equation right here, right? So from that equation, you can see that over here, next slide. From that equation over here would be D2 is 1 minus D1, right? Because D1 plus D2 is also 1. So then this is the equation over here. So that is means your I in is equal to D1, 1 minus D1 I out, right? And there should be a negative sign here because of the polarity right here. So negative sign over here, that's the relation between input current and output current. And you also know that for lossless converter is V in, V out, input power, output power should be same. So that means your I in, right, over V out, I out, it'd be what? V out over V in, right? So that means this ratio over here is also what? V out over V in. So V out over V in is also negative D1, 1 minus D1. So that it will lead to this equation right here. Okay? So that is your input and output relationship for boost buck converter. That's the same as your buck boost converter. There's no difference. It's also same as your buck boost converter. Okay. So this converter is also this again over here. So that is your current direction showing that for reverse polarity over here. So now this converter name after the original inventor, patent holder, but that patent is expired now, so anybody can build it. And also, if you look at here, your switches, like switch, this left one here, switch 1, carry the both current, input and output current, and right switch also need to carry input and output current. So that means your both switches need to be rated for input and also output current. And so this one here, this one here, this capacitor over here, need to be rated for both input and output voltage, because the voltage over across this one subject to what? Input and output. That means what? Your input is 12 volts, output is 48 volts. Sorry, input is 48, output is 12. So that one needs to be rated for at least for 60 volts. All right. So capacitor needs to be rated for input plus output voltage, and your switch is rated for more port for input current and output current. So that was saying here. So VS, your VS is voltage across the capacitor should block input and output. So that means your input and output, add them together. That will be rating of the capacitor. All right. All right. So that's what is showing over here. So look at that is VT. So that means that needs to withstand for the both input voltage and output voltage. Okay. Now let me do a quick thing over here that you know that you can do energy conservation also for this circuit here to get the same equations. So let me show you that. All right. So let me show that you can get the same equation from the energy conservation theory too. So let's see that. Let's make this one easier. Switch 1. This one for switch 2. So this is the ratio is D, and this one should be 1 minus D, right? So now the equation is we're balancing the energy across the capacitors. So 0 to dt, current through the capacitor, and voltage across the capacitor. There's a power times would be energy, right? Then plus dt to t, IC, Vt, dt should be equal to 0. There's no energy over the period in the capacitor. So now this is when switch 1 is on. When this one is on over here, your capacitor is actually connected to the output. So let's take a different color here. So when this one is on, this is your path, right? So your capacitor is carrying the output current. So output average current is I out. Vt is not changing. The voltage across the capacitor should be constant. And when this one is on here, when switch 2 is on, let me get the path here. Switch 2 is on, you're going this path over here, right? So that means you're carrying the input current. So dt to t, you are doing input current. Again, Vt is constant. Dt should be equal to 0, right? So now if I do the integration and simplify it, is I out, right? Dt plus, if V2 would be cancel out here, then over here is I in t minus dt should be equal to 0. You can take the t out now. If you take the t out now, your current would be I in would be negative d over 1 minus d times I out, right? So that's your current. And if I use this equation here, because your I in, V in is I out, V out, because there is lossless converter. So if we use this equation, and this one becomes V out equal to negative D 1 minus D V in. So you get the same equation again back by using energy conservation method for the capacitor. All right. So that's all. Again, your capacitors and switches must block the both voltage and both current. And that's all here. So we're going to do this example in the class. Then in the next video, I'm going to get into the discontinuous conduction mode.